Hey. So the expression for E is already in here, not here, in here. So it's finally actually derivative, take the derivative of E with T and the half part actually, since it's kind of like constant, it actually get. So I was wondering actually, this actually I got the idea from the book, Dove's book. So actually, also if you kind of put the value of z in here, you can kind of get there.
Okay. Can you just email me the whatever you just said, so let's see, what's the question again?
Then derivation of C.
Oh, wait, here.
Yeah.
This is question
The first
A, just to derive the heat capacity thing.
I just derive the CE version. Okay.
Yeah. Yeah, right. That's a heat capacity equation. So we got it by taking the derivative of the energy.
Yeah. Since energy is half into H and also the phonon number. So we actually, if I derivative with, I take the
I guess
derivative with
I looked
T.
through it. Just send me the thing and say it's there, or whatever, and just because when I read through it, like I said what I was thinking.
Yeah.
So
That's not the end. There's the end actually. CE is there. You kind of answer us by how the C is there.
yeah, kind of. This is 2. Huh? All right, so that here, right?
Yeah.
Your
Then
2 looks like an L from this angle.
yeah.
It's so weird. So the summation.
But that's for every mode, right? Summation is the total mode number for every mode. Summation is for every mode.
Right, that's already been.
But there's only 3 degree of freedom, so that's why it's there 3 and.
Oh, that's over the modes.
Yeah.
All right, yeah. I guess you should put an N there. It says like, or capital N,
we can actually get the capital N later when we actually say that there's number of there's.
No, I mean just whatever that you're doing, the 3 dimensions or whatever, right? 3 X, Y, Z. So that's not what the problem is, though. The problem is what it says, expression for E.
Expression for E is at the beginning of the expression for E.
No, that's the sub E, right? That's the small eta, right?
No, eta is there.
Later, go back
later.
Okay, go back. That's an E for each mode, right? For each N. So I mean each no, not
So I took that.
This is for each vibrational mode.
And I went to my.
Then
okay.
I kind of took the approach for Dope. I actually follow his code to solve this.
Okay. So but that's not the energy that you're using. You're not doing a derivative of that energy. You're going to sum that energy and get the expression with the exponential, right?
it's not.
There's the energy for the mean energy for every mode, right?
Right, but you have to
Then-
sum up
yeah.
all the
Like
modes.
without like.
Yeah, that I do it
Fire.
at the end of the end of the
And he was like,
question.
yeah, you might as well.
Yeah, but you have to do
I did it,
that.
I first I did it, I take the derivative of that.
I was like.
Then I just this since
Yeah, we
this is the
don't have that.
mean energy for every mode. I got there. Then is the total energy, total.
I guess that's the bright side.
This is the total, and then I
But just
just
say, I'll go look at Doug and see what he did, and I'll look at what you did.
okay.
Just say, and give me the page on that, it'll be pretty useful.
Okay.
I mean, otherwise we'll have to hunt it down, you know. But right now, I still don't see, like, you got the small e, that's the small e, and then you sum those together. How'd you do the, how'd you do exponentials, the Boltzmann
Side 6 months or.
distribution, right, the
I
exponential,
should try that.
the Boltzmann weighting.
Yeah.
Times that energy,
We got,
and then you sum it, and then you
Yeah,
sum
that's
that,
true.
and then you divide
I would
by
definitely
b,
see
that,
that and get at
right, so,
least some weeks out of it.
so you didn't
once and
exactly
find
do
something
that there.
I think.
pulled out first.
Sounds like you know how to do it, you know. But just-
Yes, I
Oh,
got the
that's a-
idea
that's
because
a-
I'm from physics and we kind of study those subjects.
Okay.
There's enough
All right.
computers here, you don't absolutely need.
But
No,
it's a very difficult.
Just redo it, or do it so it's clear, or
It's not
something, I don't know,
That's
send it back or whatever, I don't know. Cause it's just what I said, like, I don't see that the capital E is there. Though you have the small e, the Greek e, eta, right? For each mode, and then you have to weight each mode's energy by the Boltzmann. Yeah, you have to weight each energy, like to get an average energy, you have to weight each one by the Boltzmann divided by the Z, the sum of the states.
This is actually, this is the same approach.
Yeah, so you didn't exactly do that there, did you? Show me that you did that there. I mean, I can see that you see it here. If you want to just redo it or something, you know, if you know what's going on, I mean,
That's the end of the equation.
that's the end, so that's right, you can really get a heat capacity, and then where's your small e? I mean, your small e, then you need the big E, capital E, which is, so. This is just general expression for the average of n, right?
Partition,
I don't know what this is actually, but this isn't exactly. This isn't exactly. Anyway, you don't do the capital E. Let's see the
Really?
capital E showing up. That's fine, that's fine. The derivative of energy is the heat capacity, right? But you need to get the energy.
Divide this and then this and that cancels.
And in order to do that derivative, you have to for the energy.
The thing is that they actually did the first Lorentz distribution for phonon. They get to the, they figure out this equation.
Yeah.
Then they kind of, they can just scheme there, but the thing is that they just put the value in
I was pretty
there,
sure I wanted to do that.
in this equation. If you put the and value of it,
I think he should-
then you make the derivative, and you can get there.
But try and keep track of all of it.
No, that's the energy for each mode, right? That's why it has an N in it. That
Yeah.
total energy doesn't have an N in it.
Just so
Like
much
that's the energy,
variation,
that
things
each
that all
mode,
sound
you use
the same.
capital E, you should use small.
They're all pretty similar. Yeah, that's exactly.
All properties change.
But I mean, in the end, the average energy isn't gonna have modes in it, because it sums all the modes, right?
There's mathematical applications for them.
There's not gonna be a small n in the average energy.
So.
I mean, I mean, if you sum all of them, yeah, that's for each one. The equation you gave is just for one energy.
Put more of these
It's
advanced.
a small, in the other text, it's like small eta
I know that.
instead of e, when they sum the
But then
etas to get the capital E.
They said something bad. Anyway, this one. You guys turned it into.
Yeah.
And,
I will send you an email.
Okay, yeah, maybe just explain it in detail, and then maybe,
This is tough.
so there's a, all right, so. See, it's kind of in the notes, I guess, somewhere. So. Probably on that. Here. I mean, here's your E, right? That's E for each mode.
Yeah.
That's E energy for a mode, right? One mode of the vibration. They're gonna sum up over all the modes.
And is the integer for
You're gonna sum up weighted by the Boltzmann factor, exponential minus energy over KT is the Boltzmann, right? So H nu E over beta. There's only one energy. So you're gonna sum all those energies, the small energies. Here's the average energy. There's the energy.
For every mode.
En, no, this is total average energy. This is the energy for each mode, which is the energy that you have. See, A to N is H nu E 1/2 plus N. So you take the energy for each mode and plug it in here. You normalize by this sum of states.
Yeah.
Okay. Then that thing equals that business, and you can get this thing. So you just said this is the energy, and then you said you gave this expression, and you just gave the answer. So you need to go through this expression for the average energy, this thing. And then you need to do the derivative of that with respect to temperature to get this thing. So you didn't give this thing. You need to give that thing. 1 over e to the plus h nu e kt minus 1. See, switches because you have the e to the minus or 1 minus e to the minus. You divide by e to the minus e to the plus. You have e to the plus minus 1. That's what's missing. Do you agree that's missing? Or you need this expression to get it. You have to go from this. You have to have that expression at some point and then take the derivative of it. Yeah, you need that expression. You don't have that expression. You have like this expression. Then you're saying, you keep saying, I have the energy, but you can't take the derivative of that to get the heat capacity. You need to take the derivative of this thing. In fact, if you take the derivative of that, you won't get anything like this. This doesn't have temperature in it, for one thing. I guess that's part of the problem. Right? That's just the energy of the vibration. So it's anyway. Does that answer it, or that's something's missing in it?
I'll just look over it in here.
All right. I mean, this thing, like this is the expression you need to show somewhere in there. You can't get it without going through this. Like you have to go through this to get to that. That's the way I see it. You might, I mean, maybe you have a different way to do it, but basically, I mean, it depends if you mathematically did it or just took what Dove did and said that's right. I think that's what you did. Like you took what Dove did, you said that's right. You just kind of put it down, but you didn't mathematically. If you'd mathematically tried to take the derivative of this, the temperature, you'd find out, well, you can't do it. It would be like 0. There's no temperature dependence because that's a fixed frequency. And n is just some number, 0, 1, 2, 3. So you'd have to even pick an n in order to do the derivative. In other words, the only way you can do this is if you use this Einstein, the Boltzmann distribution. You need to use this energy distribution for each of the states. You have to use this the Boltzmann function to weight each of the states. This E minus beta H nu E. That introduces temperature, and that allows you to do the derivative thing. It's pretty hard to grade these, because you have to actually read through, unless it's like boom, 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 yes, then that's easy. But if it isn't, if you're just like fishing through it, it's not that easy. So I don't know, if you want to redo it or something, go ahead, but it's good to go through this, but basically in the end, you have this kind of weird temperature dependence. It ends up being an exponential temperature dependence, right? Because at low temperature, well, it ends up being kind of this exponential divided by t in the end. Exponential decay divided by t at low temperature. So it's not a straight power dependence. And then so it's different than the Debye, which is just t to the 3. Right. It's quite a bit different looking. Yeah.
Can you check the job chat? There is someone using the mic.
Check the chat. All right. Oh. How do you do that? I have to find out where Zoom is. Here, there. Chat is I'm missing the menu thing. I think if I do escape, it shows up. Then I can do chat here. Chat here. Wait, message. No, no one chatted. Is that what you meant?
What I mean is there is five mans in the participants, and there is someone is using their mic. There, so there's from some kind of disturbing sound is there.
Okay.
You can get there.
Okay, but everyone's muted, right? Mute.
Yeah, I think whoever was muted themselves.
Ah, they
It's fine.
cheated. All right, they cheated. Okay. Thanks. All right, so anyway, I haven't finished grading these things, but let's see. So yeah, derived Kaplans is kind of what I was just talking about too. At low temperature, it has this kind of strange dependence, like exponential over t. So you end up with, and it differs from the Debye. The Debye has t to the 3, t cubed, which he shows in the he shows kind of in this plot. Like so you have, it's actually this equation is kind of plotted here, right? So he's got so this is CV divided by t versus t squared. So that's from this equation 1. So he's got CV divided by t, and CE depends on this function, but if it was a Debye, it would depend on t cubed here. So if this was t cubed, then you have c divided by t to pull out this term, and then you just get t squared. It would be a straight line. That's why they do this plot. It's a Debye. This is kind of the Debye plot for the thing. E capacity divided by t versus t squared, like follows this equation. And then this CE would be t cubed divided by t would be t squared. So that's why it's t squared. So it should be a straight line if it's a Debye. And this is kind of noticeably not a straight line. It follows this expression, which is for the Einstein. Right? I guess he's showing the AlCO2 to show what a normal material looks like and what this kind of strange material looks like, which follows the Einstein theory at the low temperature. Again, it's like this is t squared. So 9 is 3 Kelvin, and 4 is 2 Kelvin, and 1 is 1 Kelvin. So he's going down to like 2 Kelvin in these measurements. Something really cool. Anyway, so what's that business? Then what else then here? Observed in figure 1. So basically, that's what I was talking about. This is the Einstein, that's the Debye. So distinct behavior. This one's almost never seen, and this one's like the normal behavior. And why does this material display perfect Einstein? That's because he talks about it in the paper. Basically, there's extra aluminum atoms that can sit inside these spaces. Let's see, there's a picture of the crystal here somewhere. In that crystal structure, they show a picture of kind of how, I guess the green dots are the extra aluminum that sits in the spaces of this crystal. So that at the low temperature, because those things are free, like the heat capacity at low temperature is dominated by those kind of free aluminum atoms. So they aren't strongly bound to the lattice. And they're kind of stuck in a box. So those are kind of the criteria for Einstein, is you have kind of weak coupling to the lattice. So you're not going to have, for instance, in the Debye, you're talking about like this one vibrates and then like this one vibrates, and there's a coupling between the two. So in order to get, so say this one moves left, moves right, then like there's going to be a time delay before this one moves right, like a phase difference, right? In other words, this one's moving like that, and this one's moving with a phase difference. In other words, it's got the same frequency, but it's at a later time or an earlier time. The next one will be with the same phase difference. If you go like site, there's a constant phase difference across each site, right? So Einstein says, no, they're all just shaking all along. They don't have anything to do with each other. They're just cooking in their boxes. And Debye says, well, they're linked together. But Debye says, well, in order to understand that linking together, you can consider just next door neighbors and not think to the tertiary partner over here. Or so it makes it simpler, like you just consider the binary interactions. Because if that's already a weak interaction, the next one's going to be even weaker, so you can forget about it. So that's kind of the idea of the Debye. But it could get really complicated if you had to consider all the possible interactions or go off to infinity in all directions. This will be kind of a nightmare. Anyway, so that's, I don't know if that answers whatever this says. Why doesn't Nature display perfect Einstein? It's because it's got these isolated atoms with weak springs on them, so that there's no coupling between the next atoms, so they're isolated, right? And that's the same reason that it shows. So these bonds in the lattice, the strong bonds in the lattice, which lead to a high modulus, those interfere with the formation of Cooper couples, so you can have superconductivity. In other words, they break apart the electrons that are bonded by some kind of sharing of phonons, sharing of vibrations. That's the theory. So anyway, if you have a weak connection, if the atom's weakly connected, then the electrons aren't going to be electrons are going to be free to form these coupled pairs, and the coupled pairs, because they have this shared phonon, kind of repel the lattice. They effectively have no interaction with the lattice. They just fly around freely. That's the idea, the way I understand it. Right. So this both gives you the Einstein behavior and also predicts that you could have like superconductivity in this thing at some temperature, right? -22. Or let's see, -22 is the Einstein temperature. I don't remember what the superconductivity critical temperature is. Anyway, so that's kind of how that works in my view. So in order to do that, you have to kind of figure out what an Einstein solid is, and that everyone kind of did that, I think. Then, like I've only created like 4 of these, I think. I think yours was the only one that didn't really directly do the heat capacity thing. So I don't know, you can make some argument or redo it or something if you want. I don't care really much, So, but I think you're missing something in it though. Like you don't write that expression for energy.
Book, I think they actually find the relation between both Einstein relation first.
Mhm.
Then they just plug it in the energy equation. Then they just derive it. Then they say that since the vibration is 3-dimensional and there is three degree of freedom, then that's why it's
Yeah, the 3, I don't have a problem with the 3. That's fine. And the sum, I guess it's confusing because there's 2 kinds of sums. One sum is the 3 thing, and the other one is summing over the modes. Right. So I mean that I guess you need to kind of distinguish. It would be good to distinguish between those 2. But especially when I couldn't really follow what you were doing. So then you end up with that sum, and then boom, all of a sudden you get the answer. So
it's kind of statistical mechanics.
Yeah.
It's kind of statistical physics. So
Mhm.
they are doing of things a bit different than.
Mhm. Yeah, I know somehow you have to make me understand what you did. Maybe it's a challenge beyond possibility, but like the way I read it, I couldn't understand it. So somehow it make me understand it. Anyway, so and then list the Einstein temperatures. So one group like listed the Debye temperatures. It's like they're different. They're 2 different temperatures. So the Debye temperature apparently is a temperature above which you've excited all. So the Debye also has modes, and there's a minimum mode in the Debye. So there's more than one vibrational frequency. associated with the different modes of vibration. So the minimum mode has the highest energy, the lowest index mode has the highest energy. And the Debye temperature is where you excite that highest energy mode. And then because all the other ones are lower energy, everything's excited at that point. So the Debye temperature is kind of a temperature where you light off all the fireworks in the material, everything's vibrating. And as you cool it down, certain parts of those vibrations disappear. Right. So that's kind of the idea of the Debye temperature. Einstein temperature is just related to this one average frequency that the thing has. Right. So it's not really a material property in a sense. It's just an average of all the vibrations, and like the one average vibrational frequency is related to the Einstein temperature. So they aren't the same value. One's lighting off all the fireworks, the other one's like an average of the thing. So you expect the Einstein one to be lower, I guess, than the Debye one. Because one's an average and one's the actual cutoff point. So anyway, that's the idea of those things. So anyway, and then I wanted you to say, compare it with the Kaplan numbers. You find out these are all like 244, 300 Kelvin, and Kaplan's number is 22. So somebody gave the numbers that Kaplan gave for some other, or calculated the Einstein temperature using the Einstein equation that didn't agree with the numbers that are measured. And we'll go through so you can use various techniques to get these temperatures, the Debye temperature, Einstein. You can get it from spectroscopy. Like you can do IR, Raman, and Brillouin scattering, and you can calculate these temperatures from the absorption peaks in those spectra. And then you can calculate it from the modulus. You can get these temperatures from measuring the modulus of the material. And then you can get it from a DSC or something. So you can get it, basically you can measure the heat capacity with DSC and then calculate the Einstein and the Debye temperature from the measured heat capacity and the thermal expansion coefficient, bulk compressibility. Right. So anyway, so there's at least 3 ways to get those numbers. So, and you can calculate it from the equation. That'd be a 4th way, like one of the groups did. So they aren't going to be the same value. They'll be slightly different. They'll be close. And I think, was it your group that did that or calculated thinking that it was your group, but one of the groups calculated it using the Einstein equation, didn't agree with the numbers that I put in the PowerPoint thing. So it's basically because I think the experimental numbers are taken as actual value sometimes. And the calculated value is pretty close, but it's not exact. So the 22, though, if you did it right, the way I intended this, which may not be right, but was that you had 300 Kelvin and 22. Why is there a difference? The difference is the atoms in copper, iron, aluminum are held firmly with these bonds, right? Metallic bonds held together in a structure. And this aluminum thing is just floating around in this little box thing. And this Einstein temperature is going to be related to the modulus of the system. So the modulus of that free aluminum atom within the crystal is pretty low, like it's almost 0. So it's 22 Kelvin. And the other is like 300 Kelvin. So it's because of the structure of it that there's a difference like that. That, again, that's my opinion. These things seem to be, I'm not an expert at this stuff, but that's the way I'm looking at it. Then derive equation 2. So this is like absolutely a nightmare, right? So equation 2 is like, it's like this thing. So it's a resistance, and it's related to this thing, which is a trip down memory lane, because we just had that for the average energy thing. Like average energy is like that same thing, right? That's the average energy, right? So let's see where I was here. So that's basically the average energy, missing the H nu, and then there's some constants here in capital Ni. And both of these papers, I guess in the 70s, like nowadays people define the terms when you give an equation, like at a minimum, like you define the terms that are in the equation. So you could have a rough idea like what's going on without, and you give citations to the references that are going to describe what's going on. Both they're less absent in the Kaplan paper, but they're like super absent in this Cooper paper, making it almost unreadable unless you're Cooper.
Call this a letter. I don't know, is that different than an actual like?
No,
published
it's
paper?
just
Is it like a different format?
it's a different format. It's a length. So it doesn't have like introduction, abstract,
Right.
introduction, conclusion, experimental. And it's supposed to be like it would be 5 typewritten pages. It's like a nature paper is a letter. Almost always, unless they invite you to write a review thing or something, which is, you know.
Okay.
So basically PRL, so any kind of letter thing is going to get a higher citation index than a paper. Because it's harder to get a letter published than a paper. Like a paper, you can go on and on, blah, 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 blah. And then like, but a letter has to be very concise and right to the point. And just like, here it is, that's it. You know, E equals MC squared. And like, boom, there it is. It's like,
Right.
yeah, so a lot of Einstein's things actually were letters or things like that. It's like a letter, 5 pages, 5 typewritten pages ends up being like 2 or 3. What is this? 1, 2, 2.5. And you're only allowed like 1 or 2 figures in it. And it's supposed to be like kind of cutting edge. Supposed to be something new, hasn't been done before. So certain criteria that go beyond what a paper is. Makes it like a more prestigious thing to have a letter than a paper. It's like for a person of few words, this kind of thing, and you can say something important, right? So PRL is like the premier letters journal, physical review letters. Oh, this is PRB, but it's in 74. They probably, maybe they had PRL after this or something. Anyway, it's a letter. It is a letter. And the nature paper is supposed to be letters too. So you can see it's really short. So anyway, so he said, all right, so there's a lot of stuff in here that I don't understand. Like, but if you just read around the equations, he answers the question, I think. So he says like, so the question is like, drive equation 2. All right, so all you can do with this, there's no possibility of actually doing what he does. You can find the book. One of the groups went and got the book, the Mott book or something, and then that doesn't seem to be decipherable. I glanced at it, but I didn't actually get much out of that either. So there's a and not Mott. He references someone here. Just if country Einstein oscillation of free electron gases, blah blah blah, da 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 da. The other symbols. Let's see. So he says that this is just the average energy at some point here. Square well should give a description, blah, 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 sets a lower bound, da, 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 da. This is too small here. Let's see. G, oscillator, those symbols fit. He says it in the other one. See, I'm looking at the right paper. No, this is the Kaplan paper. That's right. He just says that. This guy says the formula used, this is the Cooper paper, which isn't the Cooper pair. I don't think. I think it's a different Cooper because this guy's in Yugoslavia and I think Cooper pair was like somewhere else. Anyway, formula blah, blah, blah for an Einstein solid is this thing. So this is the energy. You already know that's the average energy. He says that is, so he explains it here. The resistivity is proportional to the total energy of the oscillators. So that average U. So that's what that is, right? And he says that average energy is the mean square oscillation amplitude. So you can think like in the Drude model, the electrons are trying to fly through kind of a pool or a, what do they call it? Bumper pool, where you have all the little things in there and those things are moving. So like when the electron tries to weasel its way through, those things like whacking it back kind of. I mean, say they have bumpers that move thermally and the electron's trying to go through to conduct, and those are causing like resistance. So, I mean, it kind of makes sense from the cartoon picture point of view. And you can also go, I kind of pointed out in the class, like the Drude model for electron conductivity, and you can kind of see where it could be in that equation because he says the frequency. So it looks, or the velocity or something or other, frequency or velocity related is a resistance, right? So I guess you can at least hand wave an argument that that's the functional form that you would get with some constant in front. Right, and that works pretty well, like, I mean, that works okay, like considering, as you're just saying, like, so he has like, let's see, resistance, so he has this like linear dependence here, okay? But it doesn't work for the Debye one, it works for the Einstein one, but doesn't work for the Debye one. That's the interesting thing here. The Debye one's a straight T to the 4, right? Straight power law T to the 4. And you remember, like at this temperature range, this is T to the 3. So this is heat capacity times T is what you'd expect to see. I guess if you just looked at this, so you say that's T to the 3, this is T to the 4. It's just heat capacity times T to get the resistivity at these low temperature range of the thing. So anyway, so that's my derivation of that. It's not much, but that's what I have, kind of just it's going to be the energy, and that's it. That's where equation 2 of Kaplan came from. And there's some other prefactors that we'll never understand, I think. They're just pretty much buried in that book that he references. Here he references this Mott and Jones book, which I got it. Someone found that book online somewhere, and you can look at it, but it doesn't help much. Then he's going to fix this problem. Like he's got a little problem here. It doesn't work in this range, right? And he's going to fix it somehow like that. So how's he going to do that? So he says a lot of stuff that's indecipherable, except that he says there's so a Fermi, there's a Fermi levels like the average energy of an electron in the conduction band. And then if you have an occupied state or an unoccupied state, that's what this K and K prime are. So the energy difference between occupied and unoccupied is h nu. That's what it kind of gets to in here if you read through this. That's what I decipher from this, So there's an occupied and so K and K represent sums over the initial and final electron states, one being occupied and the other being unoccupied. Right, so the transition is h nu. And then blah, 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 blah. Then he just says that h nu gives them the probability, the normal probability function for h nu over divided by z, and divided by z gives them this other term, which is this. So he has this e to the theta by t minus 1 is the original one, and he has this thing which is just z. That's z, 1 over that z. So this is just the probability, that h nu probability, and the h nu goes buried into these other terms. This is just the probability, in energy h nu between the occupied and unoccupied states, Fermi factor. So anyway, this is just another Boltzmann partition function business, 1 over 1 minus e minus theta. So the interesting thing though from this, okay, so look, if you divide by e to the theta t, you get e to the minus theta t up here. Then this is 1 minus e to the minus theta t. And this is e to the theta t minus 1. You multiply those two things together, and then you'll get basically the heat capacity equation. In other words, this equation is the Einstein heat capacity equation. It's got the same thermal form as this thing, right? Except that there's an extra t here, and a t in the numerator. So it's t squared, it's t. So he finds out that rho is t times the heat capacity, which is something that was observed earlier, back over in this guy's paper. So you got t to the 4. The Debye heat capacity is t cubed, and you multiply by t, you get t to the 4. So it's like, that seems to be just agrees or verifies. He doesn't mention that in here, but basically that verifies whatever Colin, whatever. What's the guy's name? Colin, whatever he found, this Kaplan, whatever he found. And then it also kind of gives you a little bit more warm, fuzzy feeling that, like, yeah, the resistance has something to do with the heat capacity. Like, in other words, they're both involving like motion of atoms and electrons, right? So somehow the two things, so they're proportional. I mean, that kind of makes sense to me, I guess. But they aren't exactly proportional to this temperature difference thing that shows up. So that's kind of a lousy derivation, but that's what I got for that, you know, I mean, it's kind of like, that's the way I see what he's, because you can't read it, right? I mean, this stuff, the stuff he does before that, that's hopeless. So you have to, I don't know, sorry to give you something that seems to be hopeless, but like when you start reading this, like, what is he talking about? And then like, you know, and then you can look in that Mott book, it doesn't help. So then you just have to kind of figure out like what are these K and K prime things he's talking about. And then at some point he actually states it. And then you can piece it together, I think, what's going on here. That he just, this is just the partition function for a weighted state of this H nu state. That just gives you the average whatever probability for that thing. And then because the electrons can go in and out of the Fermi level, it adds this component to the resistivity. They can pop in and out of the Fermi level. It's occupied and unoccupied states. All right, that's my read of the thing. And then this thing I think everyone got right. It's like just shows the magnetic field and superconductors. You have to kind of look up what superconductors are, and then magnetic field interferes with the Cooper pair. And then and why it displays superconductivity is because the bonds are weak. In other words, there's no, it's not really in a lattice. So it's kind of like aluminum atoms trapped in a little cage. And the magnetic field interferes with the Cooper pairs. That's why. So I think everyone got E. I mean, the E was kind of like look up what is superconductivity as best you can and then piece it together, kind of what this thing's about. So anyway, kind of difficult. I think if you give up easily, it's not a good homework. If you don't give up easily, it could ruin your life. So somewhere the middle ground is the best place here. Just find an answer that seems to make sense out of it. I think that's as good as you can get, and then live with that answer, and then until someone proves it's wrong. Yeah, that's kind of how you can deal with it. Otherwise, you like, I'm not sure you can really understand that Cooper paper fully. You know, I mean, you would have to be Cooper to really understand it, I think. Anyone else think that they can understand it? I mean, to me, it's like nutty. Like he gets into some stuff, it's like too much. He needs to explain a lot more. Partly he's in that format of a letter, so he's limited what he can say. So they get a high citation index, but nobody understands what they're about. That's the problem with them. But anyway, so that's that business. All right, so anyway, move on here. So anyway, so that's the end of the Einstein thing, I think. So yeah, again, like the Debye is going to be that we have, so Einstein has one, he defines like one vibration because it's an isolated atom and it's got just those springs around it and they're all the same. So it's just one frequency of vibration. So it's called the density of states. Like what's the amount that some, like frequency is really the energy, H nu's energy. It's like there's just one, like if you did spectroscopy on the Einstein material, you'd see one peak in it. You just see one vibrational peak, IR, Raman, whatever. So Raman's going to be, if the atoms move apart, they create, so it's a polarizable material. Like when the atoms move apart, you create polarization. And IR is like a polar material. Like you have to have like NaCl, so you have plus minus. When an electric wave comes in, you put a field on it, the plus moves one way, the minus moves the other. Right, so in IR vibrations do this like plus minus. You have a actual charge on the material. Raman's going to be like if you have an aromatic ring and the electrons are free in it. So they're conducting around in a circle in the ring, and you put an electric field on it, then electrons are shifted over to one side, like in graphene or things like that. So the electrons have to shift over to one side, and then the material becomes polar. It polarizes, so it's a polarizable material. So NaCl is not polarizable because the Cl holds on to the electrons and the Na doesn't want any electrons, right? So the electrons are pretty fixed. They're prisoners in the NaCl. And something like graphene or carbon nanotube, the electrons are just free to go wherever they want. right? So basically Raman's going to see these free electrons as they polarize, and IR is going to see when you have polar materials, like how the vibrations of the atoms change. In other words, they're going to move in weird ways, right? So those are the optical, two kinds of optical vibrations. And then there's acoustic vibrations that are going to be just movement of the atoms in kind of a coordinated fashion, like a wave through the material, right? You compressive and then decompress, and that compression waves moves through the material, right, at different wavelengths. So Einstein can handle some of this, right? But he can't handle most of it, because when something moves through the material, it's going to have a phase to it, right? So that the one next to the other isn't going to be the same phase, right? So you need to have something like a phase factor, which is in here somewhere. So now the slide 80 comes to mind, but that's the other class. Let's see, or that. After that. Here, all right, so this is the position of an atom, U, like X, say, X of atom N, or this is mode N. So the X position is going to be the zero position of the atom of a mode. So the zero position of the atom, this is a position for the vibration N, like N0123. Okay, so you get, if it's N0, it's the atom kind of in the center of the situation. So you have this atom, you say N is 0, so the phase shift for that is 0. In other words, it moves to the right. Well, it moves to the right, that's it. There's no time lag to it. It just moved to the right, left, right, whatever. So it moved. So there's no time lag to it. But I go to atom N+1, there's some kind of time lag. I move here to the right, that guy moves to the right a little bit later. And this guy moves to the right a little bit later, because they're hooked by springs, but there's a time constant involved in the system. Right? So in Einstein, everything is just moving crazy at the same time. No relation between them. Here, there's a relationship between this guy and that guy. Right? So, and there would be a relationship to that and that and that and that. Like there would be a phase shift, phase shift, phase shift, phase shift. And it kind of repeats, but basically you're only considering these three, because you're only considering binary interactions. So you just consider, say, the force on that system is going to be the position of that guy minus the position of the other. So that's how much the spring stretched or shrunk. And then the position of that guy minus that one would give you how much it stretched or shrunk. And these are going to be of opposite sign, those two couples. Right? So you have 2U of the original atom, and then minus the left one and minus the right one. Right? Gives you this equation for the force of a triplet of these atoms that are hooked together. You're ignoring the next one and the next one. Right? So that's kind of the basis of this. You do a force balance, you also have like the acceleration of this atom. So you have mass times acceleration equals this spring constant thing. That's a differential equation. You can solve that with a sine wave. And it's going to have these kind of, it's going to have the frequency of the thing vibrating. So if this is 0 and it's an N1, it's just shaking with a sine wave. It's just bouncing back and forth. And then you're going to say, well, if I'm moving down the line, there's going to be a phase shift to it. That phase shift is going to be proportional to the index of the atom and the atomic spacing. So A's the lattice spacing of the atom, and then Q is the frequency kind of related to the wavelength of the vibrations going on. So that's a wave vector. So it's written. This can be written K, or it can be written S, or it can be written Q. All right, so it's like 3 letters that are used for this wave vector thing, and Q is popular in theory and is popular in diffraction and scattering. And S is kind of popular in theory and diffraction and scattering. And then K is popular in spectroscopy, and then other places, I guess. Basically, if you do IR and Raman, you're talking about the wave vector, it's K. If you do diffraction, talk about wave vector, it's Q. or it can also be called a momentum transfer vector. And then S is used in diffraction too when you don't have the 2 pi. Use S. So anyway, so it's Q here, but it could be K. I guess you have to get used to, same with omega and nu, like for frequency. Omega is with the 2 pi included in it, and nu is without the 2 pi included in it. So you'd use omega with H bar and nu with, or you use nu with H bar and omega with H for Planck's constant. Like H omega would be the energy, and H nu over 2 pi would be the, or the other way around. This thing over 2 pi, whatever. So you'd use H bar as H over 2 pi. So this 2 pi thing comes in and out, depending on what you're doing with it. Anyway, so you can propose a solution to this, or you can solve the differential equation. You find out you're going to get this solution for the frequency of the vibrations, right? It's going to have a prefactor that's a modulus. The K is the spring constant divided by the mass. And then it's going to have this sign QA, Q being the wavelength of the vibration. So this is a solution. It doesn't have specific modes of vibration. It's a continuous function in this wave vector K. So we said like the dispersion relation is going to be like the frequency divided over this K. So this is like a spatial, and this is a frequency. And the frequency is energy. So this is how energy is distributed over these kind of wavelengths. Right, and it's a continuous function, the sine function, right? So the continuous function is, so what this is like if you had a guitar string and threw it on the table, it can absorb any energy you want. It doesn't play a song, right? It's just going to be like any energy. So if you constrain it though, you fix it 2 ends, then it can only have certain, so this thing can only vibrate at certain frequencies at that point. And then this, it's still got the same functional form, but it's got selected vibrations of that form that it can, where it can vibrate. So you need this idea that, yeah, you can have this energy or force balance, and you can solve it with a sine wave. It's gonna solve that, and the sine wave depends on the wave vector. But then you need another piece of information. You need a closure to this. You need to have closure. You need to have like either fix the 2 points at the end, make it into a loop, something, make a crystal out of it. Something has to hold it together to get the modes out of it. Like an atom floating in space doesn't have modes. Atom in a crystal has modes, right? So the modes come from the fact that you're confining it somehow, right? So anyway, you can compare directly like this dispersion relation. So Einstein just has one frequency. It doesn't matter what wave vector. It's just got one number. And this has this kind of weird behavior. So it's a sign when you get to small values, the argument becomes the argument. So at low wave vectors, when you get near 0, then this thing becomes QA, and then this thing is just K by M. So you have Q as K is Q here. So you get a straight line when you get near 0, and the slope of the straight line is a modulus, square root of modulus. Right, so you can get, if you know the modulus, you can predict this energy dispersion relation. If you know the energy dispersion relation, you can predict the modulus. And this dispersion relation is related to the heat capacity through an integral of this thing. So basically everything fits together. If you know kind of what's going on, you can predict every property of the material from this kind of model. It's a thermodynamic model, and the vibrations of atomic level things. And then anyway, so that's kind of where this is coming from. So this is directly from Wikipedia. So Wikipedia doesn't have any of this stuff. It's kind of strange, which this part seems to be the major part of the thing. Like getting this sine function seems to me to be the main part of this whole Debye derivation. And Wikipedia skips that and just says like, goes through this pretty simple. So Wikipedia has 4 derivations of this. They're all pretty good. And they're all really clear, you know. So anyway, so the simplest one, the first one they give, they call just the Debye derivation. And it goes like this, like you have a box. So in this case, the box is a line, right? So to make it simpler, so you have all these vibrations. So the shortest wavelength vibration you can get is the length of the box divided by n, which means you have a vibration for each atom independent, right? So that would be the shortest wavelength. right? And that would be the highest energy, the highest frequency, vibration, right? So E is h nu, so 1 over lambda, if you have the shortest wavelength, you have the highest energy. And if you have this kind of box picture, this is in 1D, but it's a box within atoms, you can calculate what that energy is. Like, it's going to be the E equals h nu, so you have h, and then 2L, lambda's 2L by n, so you pop that in, and the other speed of sound in the solid. Gives you the energy for that, for each of these vibrations, each of these kind of oscillations in the material. And then, so yeah, you can add up those energies in 3D and then get the, easy to find the minimum because it's just going to be one atom with vibrations, right? So you can get that, and that also gives you the maximum mode. So the mode of this thing, the maximum mode would be like, if it's in 3D, it would be cube root of n would give you the number of dots in the line, basically. Right, so that's a maximum mode number for the system. Anyway, so that's kind of how this works. That'll give you this kind of dispersion relation that looks something like that. I mean, all right, so this is the idea of trying to get this kind of dispersion relation and a cutoff at this frequency where this highest energy modes is activated. So if you have that amount of energy, you can activate all the modes, right? Down to n is 1, and then n is 0 means translation of the whole object. So you get to n is 0 in this picture, you're moving the object around the room. Right, so anyway, so let's see if I can move this around. All right, so the yeah, so we have this K thing I mentioned before. These notes are kind of messed up, but so we have this idea that so K is 2 pi over the wavelength, then you have two sizes, A and lambda. So if lambda is bigger than A, so that means what K is 2 pi over lambda, so you're at K is smaller than 2 pi over A. So 2 pi over A is defines a Brillouin zone, then this K can go to 0. Right, so that's where you get the modulus out of this thing. So basically K's inverse, like the bigger K is, so if you have a so the red line is lambda's a small number, right? So if your lambda is smaller than A, right, then you're outside of a Brillouin zone. It means that anything larger than that, it's only going to be interpreted by the atoms, right? And the atoms can only vibrate at a certain frequency. So anything you put in a higher frequency is going to be converted into a frequency for the atoms. So the atoms are like a translator of the applied frequency to this Brillouin zone frequency. Right. So you can see the two are related, but basically this makes sense only really if you have lambda larger than the atoms. And then you can get the atoms moving with the applied wave and not with some kind of derivation of the wave. So everything at smaller wavelength is just going to be translated into the larger wavelength by the atoms. So basically it's going to repeat in space with this inverse space kind of repeat rule. So you're going to end up with like a lattice, just like the Bravais lattice for diffraction. So you're going to have the atoms vibrating, then the atomic spacing A, or the Brillouin zone spacing 2 pi over A, right, from this. So lambda would be A. And then basically you're going to form a lattice of those in space. So that the larger distance is actually smaller, and the smaller distance is actually larger. So when you get to the large 0 point of this thing, then if it's absolutely zero, you're actually moving the object around the room. And then if you get larger than zero, you're doing the largest vibration you can do to the thing. Because it's the smallest number, so it's the largest wavelength. Right. So that largest wavelength is like you're stretching it. So that's the modulus. Right. You're actually like picking the thing up and you're moving it. So that's going to be the modulus. Right. And then at the lower vibrations, you're kind of doing a sonication of the thing, like internal to it. Right. So anyway, so you go to higher Ks, you get smaller sizes, you get in these like sonication of the material. Right. And then so you're gonna have this Brillouin zone is gonna form a lattice that looks a lot like the Bravais lattice, and it's gonna be a lattice associated with vibrations. So if for a mechanical vibration, so an acoustic phonon, you have this limit when you get to zero that the thing moves around the room and it's not really vibrating anymore. Like you threw the baseball across the room, it's not a vibration, right? So that's why it goes to zero at K equals zero, the acoustic phonons. For the optical phonons, so again, like you can think of like NaCl, so you could have an optical phonon that, like you're exciting with an electric field, Na plus and Cl minus. Say you go to this large wavelength vibration, so you actually move it. So what you're doing is actually moving the ions, you're polarizing the material. So that's got to do with the dielectric constant. Like it polarizes. Like when you just put a field on it that's not oscillating, it polarizes it. Right? If you just put a force on it, it throws it across the room. So it goes to zero K, like for acoustic phonon, it goes to zero at zero, and the slope is the modulus. The optical, you get to kind of the dielectric constant in the middle, and it's flat. And it's got a value, right? So the two kinds of phonons are going to have like this behavior. Like you have this kind of flat behavior for the optical in the middle, and the acoustic goes to zero. And so you can tell right off the difference between optical and acoustic. So optical you measure with IR Raman, and acoustic you measure with sonic, right? Both are contributing to the heat capacity. So you have both of those kinds of vibrations, and you also have the electronic contribution. There's also a magnetic contribution to the heat capacity. So this piles on, right? But so basically, when you start talking about vibrations, it gets to be like there's no optical Einstein modes, I don't think. Right, so you have to be talking about oscillatory vibrations. I don't think there's Einstein doesn't break apart into these kind of different types of vibrations. This is Debye stuff, right? So if you follow the Debye thing through a lot of math, I think this is linked to the actual math, possibly. Lattice dynamics, blah, 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 blah. And then they finally get to that K equation, so this equation. There's some math involved. Basically, plus and minus. So if this is minus, and you go to K is large, then somehow this term drops out because sine goes to zero. Then you have this square root of that thing the same as that thing, so it goes to zero. So if this is minus, that's an acoustic phonon. This is plus, then this thing isn't zero. Then these two cancel, and you end up with just that part, which ends up being the dielectric constant. That's the peak there. Right. So anyway, this link to that if you want to look at it, but in fact that picture is stolen, I think, but there's a lot to it. So let me just get back here about that thing going nuts. There's actually two things here. That one. Yeah. All right. So let's see. Oh, and then these modes, okay, are going to be so optical modes n like how many atoms? So 3n minus 3, and then acoustic modes 1 longitudinal, 2 transverse. So there's a fixed number of these modes. So you can count up like how many modes you're going to have, and then you're going to end up with a spectrum like somewhere here. There's some spectra in here somewhere. Here, all right. So So this is longitudinal transverse, these are just acoustic modes, right? Longitudinal transverse means it's like a guitar string wave, and longitudinal means it's like a compressive wave, like what you think of as sound, I guess, for me. Right. And then they go to 0, so those are acoustic modes. Like they go to 0 at 0, all of them go to 0 at 0. So the way it's plotted, so you can see it's going to repeat itself on the other side. So they only show one half of it. And you can see this for the 100 type planes. This is 110 types and 101 types. Right. So basically, those are kind of acoustic vibrations you get. Someplace it's going to show optical, a table of optical. So here's one where it's longitudinal optical, transverse optical, longitudinal, and this is for copper CuCl. So because it's got this polarized, Cu's plus, Cl minus, and then so it's got these optical modes in it. Whatever the other thing was, it didn't have optical modes. Right. So you can see the optical, when it goes to 0, has a value, and this acoustic ones go to 0. Right. And the slope is kind of the modulus, I guess, associated with the whatever kind of crystallographic plane it's associated with. Right. So you're going to have like all these modes of vibration, and then you can convert that to this density of states through kind of an integral function, right? So it's basically density of states is like how many. So if you have frequency, so density of states is like the spectrum, like the IR spectrum, say, or whatever. It could be a Boolean spectrum, can be Raman spectrum or IR spectrum. They're all sensitive to different kinds of vibrations, right? But they're all doing the same thing. They're all looking in terms of frequency, or you can convert frequency to wave number, and then how much material is vibrating at that wave number, right? Associated with certain kind of motions of the atoms, right? And then you can convert that to the dispersion relation. From that, you can get the heat capacity. So that's kind of the idea. You'll see like these things all coupled together in the papers. Let's see. So let me go back in time. So somewhere here it talks about the constraints to get the Debye thing. Debye model. Dispersion curve. This is just showing what longitudinal transverse waves look like. This is that equation. That doesn't help any. I'm going to solve this thing to get. Oh, this is right. This tells how to convert to density of states to get the dispersion relation to get the density of states. That's next. First, I want to go through. I'm not sure why this is like randomly arranged. There's so many books on this. I think it's early on here. These things are like mixed together. Right, that we've been through. Sorry to do this to you. That we did. I'm looking for the thing with the constraints on it. This is not it. That's not it. That's not it. It's all Einstein stuff. This is what we did already. That's the Debye model. This is close. Just looking at this morning. I'm looking for the derivation of the Debye equation. It's not here so far. Remember. Oh, here, yeah, this is it. All right, so choose periodic boundary conditions. So you're gonna have that series of atoms. And you say that the velocity, so this is like a guitar string. So you say at the beginning and the end, they're in phase with each other. So the u of x equals 0, u equals L. Like a guitar string, the phase is the same at the two ends because you've tethered the mode, so the thing is actually fixed, it's not moving at the two ends. Right. So, or you could say another closure. So this is a closure relationship. Another one is that it's a loop, so it's the same thing. Like if it's a circle, it would have the same phase at the end because it's the same atom. Beginning and the end of a loop is the same. Right. Those are the two common closure relationships. Right. So this is the kind of the guitar string closure relationship. Both will give the same answer. There's a factor of 2 difference between the two. But so then so this is a wave equation, right? And then if you say at x equals 0, then this thing becomes 1, and you just have the amplitude for the position at position 0, and then put in position L, and it has the same u. Then you can solve that for what q is. So you say 1 equals e to the I ql, and then you can solve for log of 1 is 0, and then IQL equals 0, and then you can somehow get Q is n over 2 pi over L because you know somehow this works out. This only works if you have Q is n over 2 pi over L. Right, so that gives you the relationship Q is K, right? So the relationship between the wave vector and the modes. Right, so that's basically a dispersion relationship, just like we had that the frequency was going to be sine of the mode, whatever, some mode function. Right, so that's how how you solve the wave equation, is you have to put in a closure relationship. So you can plug this back into the sine wave and get this done here. Density of states. Oh, let's see where I did that here. Well, you have to pick up on this later on, I guess. This isn't exactly coherent. Hey, why don't I look at the homework for next time? Basically, the homework is asking you to do what I didn't do. So let me escape this guy. This guy. It's a paper, it's another old paper, 2006, but he's looking at different allomorphs of like carbon and boron nitride and saying what the modulus is for the different materials, and like getting the heat correlating with the heat capacity, and he's using the Debye, like this Debye function for the heat capacity. So, and he's showing the frequency versus wave number, like acoustic and optic modes, and then converting that to the energy distribution curve, dispersion. This dispersion, that's the what? That is the density of states. So he's got the density of states coupled with the dispersion relationship, measured spectroscopically. So it's a pretty good paper. And he's got the comparing diamond graphite things in here. So that's what this week's about. It's kind of just one paper too, so it isn't like coupling things. And I don't know. There's one thing that I wanted to, yeah, since I'm stuck here, I wanted to forget where that was. Phase value surfaces. We had a the end of this. Put this thing in here. It's still there. No. I'm sure it's on surfaces. Maybe it's not surfaces. That's it. Enthalpy formation. Maybe that's what it is. Yeah. End of this. Not good. What is the thing I'm looking for? At the end of this? I added a slide that because we had that homework where we did the well, I can just do it. We got 10 minutes, right? So this is not on subject exactly, but we'll just do that. Somewhere in the notes, this is there. We did, I mean, I just wanted to show this because I figured it out the other day. So you have the correlation function, right, at low size is proportional to the surface to volume ratio. That's the issue. And then we said like that because it was some problem where there was no surface, right? It was a spinodal and it wasn't supposed to have a surface, but he showed G of R versus size, and he shows like a linear part to it at the low end, like 0, right? And kind of the slope of that's the surface to volume ratio. And then it's going to have peaks and things in it out here, right? So that should go to 1, right? So anyway, so why is that? That's pretty easy to do. So if you have some object and your size R is below the size of so R is much smaller than the size of the thing you're looking at, right? Then you can say like, oh, if I put the particle, so it's going to be like a rod throwing experiment. So you have a rod with 2 ends. So the probability of finding a rod at one point is just the volume fraction. And then the probability of finding at the other end of a distance R, right? Well, if it's within the particle, it's 100%, right? So that's kind of like the volume of the particle. And then if it's outside the particle, well, that's 0, right? This would be 1, that's 0. And you have this situation where it's at the surface. You have a surface kind of size R of the thing, right? So then that would be 1. That would be 1 if you were like in that situation. So you have phi, probability of getting 1 in is phi. And that'd be 100% if it was kind of like this situation. And it's 0 if that, so you don't need to worry about that. Then you have this situation where it's like crossing half over. So this thing is basically the surface area of the thing. So probability that you get like that situation, you have to subtract off. It's the surface to volume ratio, basically, of the thing. So that gives you this dependence of R on the surface to volume ratio times R, because this size is R. So it's like how much of this, well, you probably have that guy falling in there. If the first one is in the particle, so that's phi. And then is it going to be in this interfacial region, right? So it'd be minus the surface area of the thing times R would give you this area. In other words, let's probably be in that area. So you have to subtract that off from 1 to get the volume of like it being that way versus this way. So this would be 1 minus that. So it has to be linear in R, and in the slope that has to be surface to volume ratio for that correlation function. This is called a rod throwing exercise. So when R gets larger, it doesn't matter about the particles. It's just like, this is just the volume fraction. So usually this thing's normalized by the volume fraction, so it goes to 1. when you get, so if it gets so large, right, then it's just the probability of that one hitting a particle is going to be just the volume fraction. So you expect it to go from like 1 when it's down here, then the slope of S by V R in that region. Once it gets out here, it should just be volume fraction. So the correlation function. But just the probability of going here is the problem, because this thing's usually normalized by volume fraction. This part comes out. So anyway, that's that thing. I meant to mention that before. That was in one of the earlier homeworks, So anyway, it's possible to just do that pretty easily. All right, let's quit. That's all I have today. So this is questions. I guess we only have like 4 weeks left or something, right? Like it's not much with Thanksgiving, and then we end like December, first week of December. So it's just November. Basically, we don't have that. There's not, because I only go up to 14 homeworks. I think the 14th is like a final kind of. And we're on homework 10. So that means we have 4 more weeks. Yeah, all right. So we'll maybe finish heat capacity this week, and maybe this. There's a lot in this chapter, so anyway, and then there's just some simulations and things, and maybe we'll have time to do some experimental stuff. So